Stochastic process. What is stochastic process? The stochastic process is just a random variable, a sequence of random variable, x1, x2, xn. It's a sequence of random variable. Sequence of random variable is called stochastic process. Actually, not perfectly okay. It is actually stochastic process is a collection of random variable. It may not be sequence. It may be any set. It may be uncountable set. There are two type of just a sequence, discrete type, and the one is continuous type. So sometimes write xt such that t belongs to some index set t. Now t may be integer set. If t is integer, then it is a sequence. Not integer, it is just natural number. If t is natural number, then it is a sequence. x1, x2, t equal to 1, x1, t equal to 2, x2. Now, if t is any maybe whole real number, maybe whole integer, then it is x0, x minus 1, x minus 2. These are all random variables. Just a collection. But in our syllabus, we mainly deal with the sequence of random variables. And one or two topic on continuous time. It is also called time. This is called time parameter. It's actually time series also a stochastic process because it's a time series also a sequence of random variable with respect to time, index time. Now this x size, this x size, the spec of this x size, that means the range of this x size, the values what is taken by x size. This may be discrete, this may be continuous again. Maybe x1, x2, xn are sequence, but x1 can take any real number. So there are two variables actually. One is index variable, this t, and one is xt itself. So there are all sort of combinations. T is say natural number, so it is sequence of random variables. And x1, x2, x, these all are say discrete random variable, maybe finite random variable, only takes only 0 and 1. x1 takes only 0, 1, bound only. x2 takes only 0, 1, bound only. Maybe all IID, maybe all independent but not identically distributed, maybe identically distributed, not independent. So this is called state space. State space. So two things. The outcome of this all random variable, that the value taken by the random variables, is called state space, and this index is called index set, time parameter. Now in our syllabus, mainly state space are finite, and sometimes it is infinite, countable, and one or more two topic on is whole continuous thing. So there may be the most complicated part is the time parameter is also continuous, and this random variable also continuous. Easiest part is that easiest type of stochastic process is the sequence of random variable, and every x1, x2 are IID, may not be IID. IID is a more simpler case. It is not IID, but identically distributed with only two values, 0 and 1. Not IID, independent. So most interesting, and there are some easiest example on that. Just say x1 is 0 or 1, x2 is 0, easiest. But the most interesting, non-trivial but interesting, but not hard. It's easy but non-trivial is random walk. So we start with random walk. Start with random walk. So Actually, the stochastic process is a good example is random walk, and actually a concept of stochastic process and the idea of stochastic process actually came from the random walk. What is random walk? So, so random walk on Z. There are several random walk. Random walk on Z. That means your state space is Z, and it's a sequence of random variable x1, x2. So time parameter is now xt. Time parameter is natural number, but the state space is Z. Okay, we start with say x0. We include x0 also. So it is natural number union 0. So starting point is x0. So this is state space. This is 0. This is the 1. This is the -1, 2. All the natural numbers are in right hand side. All the negative integers in the left hand side. And say your x0 is maybe any number on Z. But okay, we start with x0 equal to 0. Maybe x equal to 5, maybe x equal to -2503. But we start with say particle start at 0. A particle start at 0. So now is x0 is not a random variable actually. X0 is 0 with probability 1. So a particle moves in Z. These are just state space. So a particle moves in Z, moves in Z is, but that means all the x's can take value only integers. And the starting point is starting at 0. That means at time 0. So we include also 0, x0. So time parameter is natural number union 0. The x0 is the starting point. It may be 3, it may be -1, it may be -8. So for simplicity, we take x0 equal to 0. So where does particle start? We call that is 0. That means probability of x0 equal to 0 is 1. Now how this particle moves? When the particle when the particle at I, when it is I, obviously I in Z, it maybe I may be 19 -13. So particle at say -13, xt equal to -13. When the particle at I, when the next step it can go to the I +1 or I -1. So it can move, the particle one can move, it can move, it can move at I +1 or I -1. That's why the random variable. If it moves only at the same direction I +1, it is not a random variable, just a random just variable. Now since it is can move I +1 or I -1, one step forward or one step backward, it may go here, it may go here with some probability. That's why it's a random variable. It's not only a variable, it is also random variable. The next step, the next position is variable. It may be I +1 or I -1, depending on the previous step is I, previous position is I. With probability P, so probability of to move at I +1 is P, and probability to move at I -1 is Q, which is 1 minus P. And these probabilities are called transition probability. transition means it is just transit, change the position, transition probability. Obviously, P or Q and greater than 0. It may be 0. If it is 0, then it is not interesting. Again, it is a deterministic. Is no randomness is there. So we take PQ is positive, and obviously less than 1, because if Q is positive, that is 1 minus P is positive. That means P is less than 1. So if PQ positive, it automatically implies that PQ both are less than 1. Now, so this is a stochastic process now. X0, X1. This is actually stochastic process. Actually, you can omit X0 also, because X0 is deterministic. You can start with X1. So X1 may be 1 or 2 minus 1. With probability 1, P it is 1. With probability Q it is minus 1. X2 may be what? 0, 2 or minus 2. X2 cannot be 1, because if X1 is 1, then X2 is 2 or 0. If X1 is minus 1, then X2 is 2, minus 2 or 0. So value taken by X2 is 0, minus 1, 2. Similarly, for 3, X3, you can check it is minus 3, minus 1, 1, and 3. Only these 4 values. For X4, it is minus 6, minus 4, minus 2, 0, 2, 4. Symmetric about the origin. So how do you write this mathematically in probabilistic sense? So xt, what is xt? So xt is the, where xt is the position. Now this is random. This position is random. Only for x0 it is not random. Otherwise it is random. Position of the particle at time t, the position is xt, and t is in natural number only in 0. Just you can omit 0 also, but okay, this no big deal if you put x0 or if you avoid x0. Now, what is the mathematical formulation? Obviously, the first initial position is 0. That means you can start with any other k. Then all the values will be just translated by k. If you start from k, then it is k plus 1, k minus 1. Next step it is k plus 2, k, k minus 2. So it is just to complicate this thing. It is mathematically is same actually. The notation will be complicated, but the mathematically is exactly same. So we start from 0. And what is this? The next, the moving probabilities. The probability of xt plus 1 is equal to maybe I plus 1 or I minus 1. If it is I minus I plus 1, given it is actually conditional probability, given that it is in the I. In the tth time it is I. If tth time it is not in I, say it is I minus 1, then probability of xt plus 1 is equal to I plus 1 is 0 just. It is P. And probability of xt plus 1 is equal to I minus 1, given that xt is I, it is Q. Any other? Otherwise, the probability of xt plus 1 is any other j's, given that xt equal to I is 0 for all j not equal to I minus 1 and I plus 1. If j is not I plus 1 or I minus 1, the probability is 0. And this actually mathematically describes our setup. Now, the important observation, this is the most important observation. What is the most important observation? Important observation is this: probability of xt plus 1 is equal to j. J may be now I plus 1, I minus 1, any j, given that xt is equal to I and xt minus 1 is equal to small xt minus 1, xt minus 2, is small xt minus 2, dot 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 x1 is equal to 1, x1. Now all this j I xt minus 1, xt minus 2, all these are integer, all these are integers. And obviously t is greater than 1 and t is now natural number. T is a time, t is natural number, t may be 1. We just avoid t equal to 0, then that is easy case. So probability of x1 equal to j given x0 equal to 0, that we omit that case. So we take t greater than t equal to 1, t may be 1, right? T may be 1, t may be 1, t may be 0, but if t0 is the only one case, so t greater than equal to 1. Interesting, this is same as this probability is xt plus 1 j is equal to j given xt equal to I. You can forget the previous, the past. No need of knowing what in the past. So finding the probability of the future, the one step forward, condition on the present and past, it is just depend on only on the present. Because if you know at xt is 7, you can find the probability of xt plus 1 is 8, xt plus 1 is 6, and any other than 6 and 8 is 0. No need of knowing x5 is 7 or 8, x3 is 0 or 2, x1 is minus 1 or 7. No need of knowing that. So these two probabilities are same, provided the important part is provided the probability of this conditional probability must be non-zero. Maybe if it is 0, then it is undefined. Then the conditional probability is undefined. Provided this is non-zero. The first easiest example is say this: the probability of say x2 equal to say x3 is equal to, oh, that's why we need t greater than t greater than 1. Oh, otherwise, right. You put t greater than 1. Because if t is 1, then x2 equal to j given x1 equal to I. So no need of nothing called past then. So there should be three random variable. One is past, one is future, one is present, and the past may be 1 or 5 or 10. So at least three random variables should be there. So that's why we take t greater than 1. So t equal to 1 case, we can't take t equal to 1. We can take, but then no question of past. So to omit to drop some variable, we need 3 variables. Because in a condition there is only 1 variable, there is no question of dropping. Probability of x equal to x given y equal to y is same as probability of x equal to x given y equal to y. No need of dropping there, because there is no variable in condition, only 1 variable is there. So x equal to say, or maybe I just put x say 100. X100 is say 70, given that x99 is say 69 and x98 is say 70, or x97 is say 769, x98 96 is say 68, is same as x100 at 70, given that x99 is 69. Because we know x99 is 69. So no need of knowing what x98. So if it is also if probability of x100 equal to 70 given x99 equal to 69 and x98 equal to say 68, then also this probability is same as this. But obviously, uh, if you take probability of x100 equal to 70, given that x99 equal to 69 and x98 equal to say 60, then it is undefined. Undefined. Why it is undefined? Because if x98 is 60, x99 equal to 69 is probability 0. So conditional probability is 0. Then probability of A given B, if probability of B is 0, it is undefined. So you need to define, we need this condition. This condition we need only for the definition, not for this result. To define left hand side and right hand side, we need this condition. Once this left hand side and right hand side is defined, to define this left hand and right hand side, we need this right hand condition, this condition. But the equality, this equal, this left hand side equal to right hand side. For that, this condition is not needed actually. This condition is needed for this, should not be undefined. Once it's defined, this are equal. Similarly, probability of say x100 equal to 70, given that x99 equal to say 68, x90 actually cannot be 68, it's a 67. The odd value must, odd the index must be take the odd values. X1 is odd, x2 is again even, is 0, 2 or minus 2. X3 is again odd. So given x898 is say 66, this is 0, because this actually this is probability of x100 equal to 70 given that x99 equal to 67. So it is 0. So if you replace 66 by any other value, say x100 equal to 70 given x99 equal to 67 and x98 equal to say 68, then also it is 0, because same probability. But remember again, if probability of x100 equal to 70, this 99 equal to 67, and say x98 equal to say 60, then it is undefined again. Similarly, if you take x100 equal to say 70, given that x99 equal to 66, something x99 equal 98 equal to say 65, this is again undefined, because this probability is conditional probability is 0. x99 cannot be 66. So conditional part is 0 probability, so it is again undefined. But if probability of x100 equal to say 71, given that x99 equal to say 69, this is 0. Why this is 0? Because x100 cannot be 71. Again, if x100 equal to 71, given that x99 equal to 70, then it this is undefined again. Why it is undefined? It is not P. Why it is not P? x99 equal to 70, then x next step is 71. No, it is not P, it is undefined, because x probability of x99 equal to 70 cannot occur. It is sort of 0 by 0 form. The probability of x100 equal to 71, x99 equal to 70, this is 0. Divided by probability of x99 equal to 70, this is also 0. 0 by 0 form. That's why it's undefined. So once it is defined, this must be equal. So what is the interesting case? The interesting thing is probability of xt plus 1 equal to j, given that xt equal to I and xt minus 1 is something 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 up to x1, such that these are defined, then this equal. So this is the most important observation and most important property of the random variable. This for all I and j and all t greater than 1, provided obviously provided the provided both sides are defined. This property is called Markov property. Next we see what is Markov chain. This is the most important stochastic process called Markov chain. And once this any chain means the stochastic process, the sequence of sometimes this sequence of random variable, which is stochastic process, is also called chain. Sometimes it's called chain. Chains means is a stochastic process, but special type of stochastic process is a sequence. The time parameter, the indexing parameter is not continuous, it's discrete. Markov property. And once some stochastic process or chain follows this Markov property, is called Markov chain. With something is extra. So for Markov chain, there is something extra is called transition probability, also stationary. May not be. Here is the important part: is the transition probability is stationary. What is the meaning of the transition probability is stationary? The one important part is also this: the probability of xt plus 1 is equal to I plus 1, given that xt equal to I is p, and this p does not depend on t. Important part is this does not depend on t, not depends on the time. The transition from 0 to 1, if x0 equal to 0, then probability of x1 equal to 1 given x0 equal to 0, same as probability of x9 equal to 1 given that x8 equal to 0 is same. This thing is called stationary transition probability. It's also called stationary transition. Transition when this transition thing is change this position transition probability. So what is mean by transition is the changing, and why it is Markov, because we can forget the past, and why it is stationary, because this probability does not depends on t. So maybe there is a Markov property, but may not be just stationary. Then it is not a Markov chain. Maybe this depends on the time. At time 7, transits from 8 to 7 to 8 is not same as at time say 11 transits from 7 to 8. That means probability of x12 equal to 8 given x11 equal to 7 is not same as probability of x8 equal to 8 given x7 equal to 7. If it is not so, then we can't say it is a Markov chain. It is not a stationary transition probability. It is a transition probability, but not this transition probability is not stationary. And if it is depends on the all past, then it is not a Markov property also. So Markov property, that means if once the present is given to you, we can forget about the past to find the probability of the future. And what is meant by stationary? And this probability does not depend on the time actually. So this random variable x0, x1, xn dot 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 dot, this random variables, sequence of random variables, is from the random walk. This is coming from the random walk. Is a Markov chain. What is the Markov chain? Is a stationary transition probability, Markov property, as well as chain. If it is not a it does not have the Markov property, no question of stationary transition probability. Question of stationary transition probability is came after Markov property. Once the Markov property is there, then the next question is this probability depends on, this probability does not depends on xt minus 1, xt minus 2, x1. Is this probability depends on t? If it is yes, then it is not a stationary. If it is no, then answer is no, then it is stationary probability. Maybe this probability depends on I and j. In that case, in random walk, this does not depends on I and j also. No, it depends on I and j. J, obviously I and j. If I equal to 1 and j equal to 2, then it is p, and if I equal to 1, j equal to 3, it is 0. I am saying that it is, say, xt plus 1 equal to 3 given xt equal to 2 is same as xt plus 1 equal to, say, 101 given xt equal to 100. These two are same. Obviously, it depends on I and j, but once j is I plus 1, does not depends on I. If j is I plus 1, then it is p. It does not depends on I again. For random walk, but for Markov chain, it may depends on I. Here it is depends on I and j both. But if j is, once j is given to you, if j is I plus 1 or j is I minus 1 or j is I plus 2, this does not depends on I. But in other Markov chain, not in the random variable, maybe it is depends on I. Maybe something in first step it can move only one step right and one step left, and the second move from x1 to x2, it may be right two step right and maybe 2 step left. Then it is depends on I also. Then it's a Markov chain. So this is the introduction of the Markov chain from random walk. Now, in this Markov chain, the important part is how do you find the joint distribution and the distribution of xn. Now, distribution of xn. Distribution of xn. What is the distribution of xn? Probability of xn is equal to I 0 if what? If mod I is greater than n, right? If mod I is greater than n, it can't be xn equal to I. So probability of x10 equal to 11 must be 0, because at 10 step it can't go to 11. If xn equal to minus 12, x10 equal to minus also 0, but it can't go 12 step left. Again, probability of xn equal to I also 0 if I and n have opposite parity. Is one is even and one is odd, then also 0. So probability of x10 equal to 11 is 0. Again, probability of x10 is equal to 7 also 0. So after even number of step, it can't go at odd integer. And if it is the same parity and this, so xn equal to I, if I and n are same parity, same parity. Both are even or both are odd. And also I is lies between n to minus n to n. It is greater than n or less than minus n, then it is 0. This is n choose n plus I by 2 p to the power n plus I by 2 q to the power n minus I by 2. Why it is so? Because to go after n step, the particle reach at I if and only if it is go I n plus I by 2 time too many step right hand side and n minus I by 2 step left hand side. Total number of step is then n because n plus I by 2 plus n minus I by 2 is n, and the difference, the right hand side it is go n plus I by 2, left hand side is go n minus I by 2, so it take the difference, it is I. So we go right I step right hand side. Total number of step is the addition of these two, n plus I by 2 plus n minus I by 2, it is just n, and the difference is I. That means, what is this? That means that is xn plus n, if we add n again, it is not xn plus n, it is xn plus n. The plus n is not in the index. By 2. This is binomial n comma p. Because in this case, if we add this with n and then by divided by 2, we get xn equal to I plus n by 2, which is this. So xn equal to, you can write this, remember this n minus I by 2 is just n minus n plus I by 2. This n minus I by 2 can be written as n minus n plus I by 2. So if we replace n plus I by 2 by r, p to the power r, q to the power n minus r, and ncr, where r is xn equal to r, xn is not equal to I. So xn equal to I, but xn plus n by 2 is equal to r. So probability of xn equal to r, xn if we say yn. So once xn equal to I, then yn equal to this r. We can take this as r. Oh, sorry, it is I. So probability of yn equal to r is n choose r, p to the power r, q to the power n minus r. That means it is a binomial distribution, and we can draw this. We can visualize all this thing by diagram. Is also called graphical representation. Graphical representation is this: starting from 0 to 1, the moving quality is p. From 0 to minus 1, it is q. Again 1 to 2, it is better I write in this way. Say it is p, minus 1 to 0 it is p, and from 0 to minus 1 it is q, 1 to minus 1 it is q, 2 to minus 1 it is q, again it is in the p, in this q, and this and this and this. Oh, arrow in that direction. Actually, this diagram say everything about this Markov chain. This p may be changed, then it is not a Markov chain. Then Markov property is old, but this is not a Markov chain because this is not a stationary probability. Then it is, since all these are p, that's a, is stationary. And this probability is transition probability also. We write transition probability. We write this transition probability like is a pxy. It is just probability of x1 equal to y given x0 equal to x. And it's the same as, because the Markov property is there, x same as xn plus 1 equal to y given xn equal to x for all n. Because Markov property. And it does not for the Markov property. It is by stationary property. Since it is stationary probability, transition probability, we can take any n. Does not depend on the n, not depend on the time parameter. It's also true for 0 also. This, so probability is of this, so but depends on x and y. But obviously depends on x and y. In this case, in this random walk, in this case, y is, if x plus 1, then does not depend on x. If y is x minus 1, does not depend on x. But any other Markov chain, not for the random walk, it depends on x and y both. And so this is a function actually. This transition probability is a function, whose output is just 0, 1 because it is a probability, and input is any two value on the state space. So now the x may be integer, z small y is also integer, so it is z cross z function from z cross z to 0, 1. So in general, this is a, if sometime we write this is a S as a state space, it may not be integers. Here it is integer, may not be, there may be rational number, maybe some finite values, some only 0, 1 or 2 maybe. Then transition probability is a function, probability is a actually is a function from S cross S, the ordered pair, to 0, 1 because output is a probability, so it is a ordered pair. What is this? This xy is probability of xn plus 1 equal to x given xn equal to y, and sorry, the other way. Xn plus 1 equal to y, it is from x to y, probability from x to y. So xn is x, xn plus 1 is y. For all n natural number, also maybe 0. And for all x, y belongs to the state space. So this is a transition probability. We define another notation. There is a notation. We define a function px. Px is a function input from z and output obviously is a probability function, so 0, 1. So for all j x belongs to z, we define for all x belongs to z. How do we define? We define px as the px at y, if input is y, this is pxy for all y belongs to z. So fixed x, if you fix x, xn equal, then this is a function of y only, one variable function. Are these two variable? If you fix x, that means once it is fixed x, that means what? That means this is actually probability of xn plus 1 is equal to y given xn equal to x. If it is not a stationary distribution, then we can write this. Then it is depends on n also. But once it is stationary distribution, is for the Markov chain, we can write this. For the random walk also, this we can write this. Does not depends on n. So now x is small x is fixed, so it's only y is the changing. So that's why this is a PMF, is a probability mass function. This is a PMF. This is a PMF. For every x, it is a PMF. Because if you take the sum, of this over y, what the state space is 1, and all these are greater than equal to 0, and the sum is 1. But remember, if you fixed y and running over x, then may not be y. But note, if you run over x, if you sum over x, this is not equal to 1. Because this your conditional probability, if you fix y, if you sum over x, then this is 1. But if you fixed x, if you sum over y, then it is not a 1. Remember that. You can check by writing this in intersection part and then divide by, because it is probability of x equal to x, intersection y equal to y, divide by probability of y equal to y. So y is fixed, so the denominator is fixed, so you can add all this numerator. But here it is, the denominator is changing. The next line, next next probability of x equal to x given y equal to y. If y is changing, the denominator changes, so you can't add just same, not the same denominator. Denominator is changing. The numerator is, you can take probability of x equal to x, y equal to you can take so everything is changing actually. Numerator, denominator both are changing. But here it is only probability of x equal to x, y equal to y, given y equal to y. If y is fixed, then only numerator is changing, denominator is not changing. That is why. So this is the PMF, but remember this p x fixed, y is changing, PMF, but if p x y, if y is fixed, x is changing, it is not PMF. The last one for today, initial distribution. What is initial distribution? Initial distribution is this distribution. Here it is just 1, but in maybe any other case we can say, okay, in starting point is with probability half it is 0 and with probability half it is 1. So probability of x equal to 0 is half, probability of x equal to 0 equal to 1 is half. So maybe it's this distribution. So probability of x equal to x, we write this as a pi x, pi 0 x also, because initially pi 0 x. So what is pi 0? Pi 0 nothing but again it is a from z to 0 1. It is a probability actually. Is a PMF. Pi 0 is a PMF. Probability mass function, because your pi 0 x is greater than or equal to 0, and if you take the sum over all pi x, pi 0 x, this is 1. Here it is only one value, but in any other Markov chain, for random walk it is the easiest. Other Markov chain may be different, for different x, maybe different probabilities. So this is a PMF. This is called initial distribution. Once you know the initial distribution, we can find the joint distribution of x1, x2 and the marginal distribution of x2 from the conditional. In the next class, we will discuss the joint and the marginal distribution of xn. We know only the starting distribution and the conditional distribution. Using the Markov property, we will see in the next class how we can find the marginal distribution of x2, x3, x4. That's for all for this class.